But I've kind of created this section because we need to know it to put everything together for limits. So we have this equation, f of x equals x minus 4 over x squared minus 3x minus 4. So I'm going to graph this on Desmos real quick. Oh, tell me what I said again. X minus 4 over... Okay. All right, and so if I graph this on Desmos, okay, I get a graph that looks like this, okay? And what we're going to be considered, I need to give you your homework sheet real quick. Okay, so if you look at this, what we're concerned with figuring out is where these graphs have discontinuities, okay? So discontinuities basically are the definition is complex, but in reality very simple. It means if you're tracing this graph from left to right with a pencil, do you ever have to pick your pencil up to trace it, okay? So like from left to right over here, we're doing this here and right here. You can kind of see, maybe not so well, but if you go down, like here, if I put in the line x equals -2, no, sorry, -1 here, that looks like, it looks like it's touching, but if I zoom in, it's not really, right? So, and that's going to be the case. So what you've got there, in this case, is a vertical asymptote. So that graph is discontinuous because you're going to have to go, you've got that vertical asymptote, you get closer and closer and closer to -1, you never touch it. Then to keep tracing, you got to jump back up to positive infinity and trace the graph from there. So you have a discontinuity here. The problem with Desmos is we have a discontinuity we can't see here as well, because it looks like it's continuous everywhere else, right? So if you look at your notes, if we find f of 4, so f of 4 just means to plug in 4. So if you plug in 4, you would have 4 minus 4 over 4 squared, which is 16, minus 3 times 4, which is 12, minus 4, which is going to give you 0 over 0. Can we divide 0 by 0? Anybody cheat and keep your phone today? Ask Siri. Anybody have theirs? You gotta have an iPhone, but Siri will tell us. Ask what's 0 divided by 0?
What is 0 divided by 0?
So Siri will tell you that if you have 0 cookies and you try to divide them among your 0 friends, that doesn't make any sense, right? And you're sad. Cookie Monster's sad because there's no cookies, and you're sad because you have no friends. But you can't divide 0 by 0. This is 0 divided by 0 is actually what we call the indeterminate form, which I think I'm getting a little bit ahead of myself in telling you that. But you can't divide 0 by 0, which tells me something's happening there. Okay? But if I look at the graph, if I go back to, oh gosh, let me flip this back because it doesn't like to do this most whenever I, oh no. If I go back, right here at 4, oh my. I'll switch it back here in a second. We'll see if it'll go. Right here at 4, it doesn't look like there's a discontinuity. It looks like it's solid, right? Maybe this is coming loose here. Let's see. All right, let's see if we can get it back. Please, don't turn purple. All right, so if you look at this graph right here, it doesn't look like there's a discontinuity at 4, where x equals 4 right here. We actually, you can almost see it whenever did you guys see it turn to undefined for just a second? Oh, right there it was. I can't. Oh, there it was again. I can't get it to actually show up, but there's a point right there at 4 where it's undefined. Okay, so we can't see it on the graph because it's just a single point, right? And so if it's just a single point, a point doesn't technically have any width, so it's going to look like it's continuous, but there is a discontinuity there. Now, at -1, we pretty obviously have a discontinuity. And now I need to know how to get back to, okay, there we go. All right, so if we plug in -1, we get 1 minus 4 over 1 squared minus 3 times 1, which is 3, minus 4, which is going to give us, hold on, -1 minus 4. We're going to have -1 squared, which is 1. Negative 3 times -1 gives you positive 3 and -4. So we get -5 over 0. Okay, so -5 over 0 is undefined. Okay, but 0 over 0 is something weirder, right? This actually, we call this indeterminate. But -5 over 0, that's just undefined. Okay. And so whether or not we get the indeterminate form or the undefined is going to affect what our graph looks like. Where we had at -1, we had that vertical asymptote. It's really easy to see from the graph that there's a discontinuity there. At f equals 4, we have something different. So it says to look at the graph. We did that. We could also look at the table. I'm not going to, Desmos is hard to do a table on, so I'm not going to do that right now. But at the table, it would show us that at 4, it would be undefined, and at -1, it would be undefined. Or at 4, it's like, it'll probably say undefined if you did it in the table on the calculator. So, there are 2 types of discontinuities that we're going to talk about in this section. The first is a vertical asymptote. The vertical asymptote, for example, if the line x equals 1 is a vertical asymptote for the function f of x, if f of x approaches infinity or negative infinity, as x approaches, I guess that should, since I put a 1 here, I should put a 1 here, from either side to the left or right. So what that means is you get closer and closer and closer to 1 from the left or from the right, that y value is going to go up to infinity or down to negative infinity. So it gives you that vertical line there that you get closer and closer and closer and closer to, but you never actually touch. Okay. Vertical asymptotes are caused by zeros in the denominator that do not cancel. Okay. Holes in a graph. The hole in the graph is like that point we've got at -4, because at +4, because at 4 it looks like it's continuous, but if you can actually go to that point at 4, it's actually undefined. Okay, these are also sometimes called removable discontinuities. You might want to underline that or highlight it or something, because removable discontinuities is a word that you might see on a test or a quiz. Not tomorrow's quiz, because this stuff is not on tomorrow's quiz. But you might see it. So instead of calling something a hole in the graph, I might call it a removable discontinuity. It's like the fancy word that we use for holes in a graph. So you might see that. You also might see it on the final exam. So so look out for that. Typically in class, I'm probably going to call them holes most of the time, because I'm not quite as fancy and formal, you know, of a math teacher as some maybe. So I like to call something a word that's easier to remember. But removable discontinuity is another word you can use for this. It's called a removable discontinuity because you could remove it, by just putting a single point there. Like if we put one tiny little point there to fill in that hole, then it would be continuous. Holes are caused by zeros in the denominator that cancel. So let's look at an example. All right, so if we look at an example, for example 1, I've got x squared plus 5x minus 6, and I've got x squared plus 2x minus 24. So if I want to know about the discontinuities, discontinuities happen when I have zeros in the denominator. Okay, so the denominator is what I care about. Right? So to find my discontinuities for this, what I'm going to do is I'm going to factor the denominator. So in this case, it's going to be x, and let's see, 6 and 4, so plus 6 minus 4. So I have discontinuities that looks awful, but discontinuities at x equals -6 and at x equals +4, because those are the numbers that are going to give me 0 if I plug them into the denominator. Discontinuities come from the denominator only. Okay? We do not care about the numerator when we're finding discontinuities. The denominator only, except if I want to know what type of discontinuity I have. -6 and +4 are definitely discontinuities. If I want to know what type of discontinuity I have to look at the numerator to see if something will cancel. Okay, so I could go up here and factor the numerator, and for this one, it's going to be x, and I'll have -1 plus 6. Does that look right? I'll give you a +5 in the middle, -6, yes. Okay, so what I've got is I've got x minus 1 over x plus 6. I'm running out of room, but I've got x minus 1 times x plus 6 over x plus 6 times x minus 4. Okay, so the numerator does not tell me where the discontinuities are. It just tells me what type I have. So if a term will cancel, a binomial will cancel, in this case the x plus 6 cancels, that tells you you have a hole in the graph. So at -6 you have a hole, or a removable discontinuity. And then at 4, x minus 4 does not cancel out of that denominator. So at 4, I'm going to have a vertical asymptote, and it's fine with me if you use VA to abbreviate that. Just make sure you know what it stands for. Okay, questions for 1? So basically you're going to factor. The x minus 1 just stays there. It does not tell you anything, because the numerator does not give you the discontinuities. The numerator just helps you see if their holes are asymptotes. So we don't say anything about that one. Okay, so for number 2, I would want to do the same thing again. I would want to factor the denominator. Work with that denominator first. How do I factor x to the third minus 4x? There's something I can do first. Pull out an x. So I have x times x squared minus 4. All right. Will x squared minus 4 factor? It will. It's a difference of squares. So this, I could mark this out. This can be x times x plus 2 times x minus 2. That's a plus 9, minus 12. All right, so I have discontinuities. That x is going to be at x equals 0. I'm going to have one at x equals negative 2, and I'm going to have one at x equals positive 2. And so let me rewrite this over here. I've got 3x over x times x plus 2 times x minus 2. Will anything cancel? The x can cancel with the x up here because it's 3 times x, not 3 plus x, so it can cancel. So that tells me that x, it gave me the x equals 0. So that tells me that I have a whole. Oh, I didn't mean to do that. Go back. That tells me that I have a hole in the graph at x equals 1. Do x plus 2 or x minus 2 cancel? They do not, so those are going to be vertical asymptotes for the graph. And whenever you do this on the final exam, you can check yourself really easily by typing it into Desmos. You'll be able to see the vertical asymptotes. The holes, though, remember, you can't see. Okay? All right, example 3. Okay, bottom's already factored for us. Okay? Matt, where am I going to have discontinuities? Negative 3. Positive 2. Are they going to cancel, Matt? They are not, because there's nothing in the numerator for them to cancel with. So since they do not cancel, these are both vertical asymptotes. Okay, questions? All right, this last one, we could factor that bottom, x plus 5. Ugh, sorry. X plus 5. Good gracious, this is hateful. X minus 1. So I know I'm going to have discontinuities at x equals negative 5 and x equals, that's a minus right there, so x equals positive 1. Okay, the numerator, how would I factor that numerator? X out first, so that's going to be x times x squared minus 2x plus 1. Will x squared minus 2x plus 1 factor? It will. X and x minus 1 and minus 1. So this is your numerator. Your denominator was x plus 5, x minus 1. So when we look at this, the x minus 1s can cancel. So that tells us that at x equals 1, we have a hole in the graph. But 5 does not cancel, so vertical asymptote for 5. Okay, questions? All right, so that pretty much covers your holes and your vertical asymptotes. The last thing we're going to talk about is really not a discontinuity, but it's an interesting thing about a graph that we sometimes need to know. And that's a horizontal asymptote. So for a horizontal asymptote, your graph is not discontinuous because as you go, like a horizontal asymptote is going to be as you get closer and closer and closer to the x-axis, you get, closer and closer, but you never actually touch. So the line's continuous. You don't have to pick up your pencil, but it still is an interesting property that you might want to know. So to find a horizontal asymptote, you're going to do the limit as x approaches infinity of the function. And in some cases, you would need to do the limit as x approaches negative infinity separately. But on the ones you're going to see from me, I don't think that's going to be necessary. If you get weird things like -2 to the n power or square roots of things, type it into Desmos and look at the graph and see what happens. But for what I'm going to give you, they're going to be fairly straightforward. So, like for this first one, we would do the limit as x approaches infinity of 9x over x squared minus 7x. And so for this, we can use that trick that we learned on Tuesday, Bobo Botno eats DC. So is this one bigger on the top, bigger on the bottom, or exponents are the same? Bigger on the bottom, and whenever it's bigger on the bottom, what is our limit? It is 0. Okay? So that's your Bobo, bigger on bottom, 0. All right, so your horizontal asymptote here, oh, remind me, this is so hard to keep straight. Horizontal lines, is it x equals or y equals? It's y equals. So y equals 0 is your horizontal asymptote. Okay, so y equals 0 is your horizontal asymptote. Okay, questions? For 6, you're going to have the limit as x approaches infinity of 12x to the third minus 8 over x squared plus 2. Bigger on top, bigger on bottom, exponents are the same. Bigger on top. Whenever it's bigger on top, that's not 1, right? That means positive infinity or negative infinity. In this particular case, because you've got a 12x to the third, that's your highest exponent, and that 12's positive, this limit right here would be infinity. But is infinity a limit? It is not. So this tells me that like the graph goes up and up and up and up forever, which means there's none. There's no horizontal asymptote. So if you get positive or negative infinity for your answer, there is no horizontal asymptote. Okay. All right, this last one, we would do the limit as x approaches infinity. I'm going to go ahead. That top part's not multiplied together, so it's going to be necessary for me to multiply those together. So that's going to be x squared plus 2x minus 9x, which will give me minus 7x minus 18 over x squared minus 9. Okay, bigger on top, bigger on bottom, exponents are the same. Exponents are the same. What do I do when the exponents are the same? Divide coefficient. So there's not any coefficients written here, but there's an invisible one there, an invisible one there, so 1 divided by 1 is just 1. So my horizontal asymptote would be at y equals 1. Okay, questions? Okay, your homework is going to be a worksheet that I'm going to give you. The worksheet is required. Didn't mean for that to go away. The worksheet is required, so you must do it. The practice quiz is not required, but highly rated. Oh, I didn't do domain. All right. So I do need to tell you about domain real quick because I forgot to do that. If we go back up to where we were looking for discontinuities, I have discontinuities, like for example 1, I have discontinuities at x equals -6 and x equals 4. So, I'll type this in here because it's easier. So I would say that my domain would be this. It would be, I'm going to have to use x, don't write this down quite yet, x cannot equal -6 and x cannot equal 4. So, except for I wrote equals because I'm typing. So, just do not equals. Just put slash through your equals. There. So your domain is really just the same as your discontinuities. It's just x cannot equal -6 and x cannot equal -4. So if you've got your discontinuities correct, then that is your domain. Okay. Questions? All right, go ahead and work on that.